This is the IEEE Computer Society Distinguished Lecturer Webinar Series, brought to you by the Distinguished Visitors Program. The Distinguished Visitors Program delivers tools for individuals at all stages of their professional careers through visits to chapters, offering opportunities for individual interactions, and to the membership through webinars by respected professionals. We have distinguished visitors who cover machine learning, cybersecurity, robotics, big data, cloud computing, blockchain, and cryptography, among others. Chapters can request a distinguished visitor on computer.org/distinguished-visitors. The Computer Society pays all intercity travel, while chapters are responsible for all costs with regard to the hosting of the distinguished visitor, such as lodging, transportation, and food and incidentals in the city of the presentation. The Distinguished Visitors Program is able to pay up to $1,000 for a visit to a chapter, but by working with other nearby chapters to develop a tour, that amount can be increased. So when your chapter is planning its next event, think of the Distinguished Visitors Program.
Hi everyone, and welcome to today's Distinguished Lecture Webinar Series. My name is Scott Levine and I'm the Membership Manager here at the IEEE Computer Society. I like to take care of some quick housekeeping tasks before we get started. You can ask your questions in the Q&A panel you see on your screen. Dr. G will answer as many questions as he can following the presentation. When you are writing your question, if it relates to a particular slide, please do your best to reference that slide. The webinar is being recorded and the recording will be made available to you following the event. As the computer vision profession evolves, the IEEE Computer Society continues to provide resources to access the latest research within the field. For example, the Computer Society Digital Library, which features over 600,000 articles related to computer vision. Additionally, resources such as our Tech News blog highlight recent trends and discussions revolving around hot topics within computing. Furthermore, computing professionals and enthusiasts can connect and grow with other members via various communities, conferences, and more. More information will be shared after the webinar, but you can always learn more at computer.org. In today's webinar, Dr. G will present knowledge augmented deep learning for data efficient, generalizable, and interpretable visual understanding. In this talk, Dr. G will discuss the development of hybrid computer vision framework that systematically integrates the well-established prior knowledge with the image data to achieve data efficient, generalizable, and interpretable visual learning. He will apply the framework to different computer vision tasks, including 3D human body reconstruction from monocular videos, human action recognition, and 3D shape reconstruction from single images. As mentioned, with us today is Chung Ji, who is a professor with the Department of Electrical, Computer, and Systems Engineering and Rensselaer Polytech Institute. He received his PhD in electrical engineering from the University of Washington. He was a program director at the National Science Foundation, where he has managed NSF's computer vision and machine learning programs. He also holds teaching and researching positions at the University of Illinois Urbana-Champaign, Carnegie Mellon, and the University of Nevada at Reno. Dr. Xi, thank you for being here today, and I'd like to pass the floor to you to get started.
Thank you, Scott. Can you hear me?
Yes, we can, loud and clear.
Okay, thank you for the invitation. And I'm very happy to give the presentation about our recent work of developing a hybrid computer vision model for data efficient, generalizable, and interpretable visual understanding. First, I would like to give a very quick introduction about computer vision. As we all know, computer vision is about developing algorithms to automatically process image or video to reconstruct, interpret, and understand a 3D scene from its 2D image in terms of the geometric, spatial, and dynamical property of the scene object. So this is a basic definition of computer vision. And there are some common tasks in computer vision include object detection, object recognition, motion estimation, and 3D reconstruction. computer vision traditionally has been model-driven, theory-driven. And over the past 50, 60 years, many different computer vision models and theory have been developed. They include the projection models, photometric models, and the motion models. And this theory and models serve as the theoretical basis for traditional computer vision algorithms. Besides the model and the theory, traditional computer vision has also used domain knowledge about the target of object. The domain knowledge may be from different disciplines, including neuroscience, biology, and physics. And in the past 50 and 60 years, this theory and the domain knowledge serve computer vision well, and they have led to success in many areas for computer vision before 2012. However, the success of the traditional computer vision tend to be incremental because the models are either too simple to adequately model real-world conditions or too complex to scale up. And as a result, since 2012, the development in deep learning has led to dramatic improvement in computer vision performance, in particular for certain computer vision tasks, such as object detection and object recognition. And in fact, object recognition using deep learning model has outperformed human performance on some very large benchmark datasets. As a result, there is a common belief, optimal belief among computer vision researchers that big data plus deep learning plus GPU will enough to solve computer vision problems. And there will be no need for models, for theories, and for domain knowledge. And our research tried to show that this is not the case, in particular for real-world computer vision systems. And here, in addition, there are serious limitations with the existing deep learning-based computer vision algorithms. The first is the data inefficient. Current deep learning-based computer vision algorithms requires large amount of data. In addition, it also requires the annotation of this data. And in fact, right now in the field, in the deep learning field, the trend is developing ever larger models. For example, at current, the largest vision transformer has 2 billion parameters, and it needs 3 billion images to train the model. These kind of large foundational models are not feasible practically because in many real-world applications, we never have enough data, and we never able to acquire a large amount of annotations. And more importantly, these kind of large foundational models are not sustainable theoretically, economically, and environmentally. So this is one major limitation with existing deep learning-based computer vision, which is data inefficient. The second limitation with existing learning-based computer vision is poor generalization. The existing deep learning-based computer vision algorithm perform extremely well on the data set that are used to train the model. However, they do not generalize well to novel data set and to different domains. And this is a serious limitation for real-world computer vision systems, because in the real world, the situation, the conditions can change, and it can be very different from this condition in the training data set. And the third limitation with existing deep learning-based computer vision algorithm is lack of interpretability and performance guarantee. The existing deep learning-based computer vision algorithm are typically trained end-to-end. And there are little interpretation or explanation about the feature it learns and about its prediction. And more importantly, the existing deep learning-based computer vision algorithms are not able to accurately quantify its performance. And this, again, is very important for real-world computer vision system, which require to guarantee its performance and to reliably quantify its performance under different conditions. So these are the serious limitations. and there are existing efforts try to address these limitations. However, existing efforts have only achieved incremental progress, as we say, incremental progress, because the existing efforts are typically still data-driven. So we are looking at the addressing or mitigating this limitation from different perspectives. We are talking about the inject prior knowledge, well-established prior knowledge from different disciplines to address or to mitigate these issues. Before I introduce our solution, I want to give you a side-by-side comparison between traditional model-based computer vision and the learning-based computer vision. So for model-based computer vision, it is model and theory-driven, and it can effectively explore prior knowledge. And it is explainable, it is data efficient, however, it cannot scale up well, and it requires strong assumption for some models or theories. Learning-based model, on the other hand, is data-driven. It scales up very well, and it performs extremely well on within dataset. However, it is data inefficient, uninterpretable, and cannot explore prior knowledge. So our goal is to develop a hybrid computer vision model by combining the traditional model-based with the current deep learning-based approach. So this is what we call the knowledge augment computer vision. And it is our belief the long-term or ultimate success of real-world computer vision requires a union of prior knowledge and data. And for this, we propose a hybrid vision model that combines model-based computer vision with deep learning-based computer vision to leverage their respective strengths and to avoid their respective limitation, and also to ground the deep visual learning in the well-established prior knowledge. And through this hybrid vision model, and the prior knowledge and data work synergetically to produce computer vision algorithms that are data efficient. Because of the use of prior knowledge, and the prior knowledge is transferred to the deep model, this will reduce our dependency on the training data. And it is robust because the prior knowledge can significantly constrain the solution space. As a result, the prediction can be more robust and more accurate. And it is generalizable because the prior knowledge that we propose to use is generic, well-established, applicable to different situations, different domains. As a result, the model trained using the prior knowledge can better generalize across domains. Finally, it is interpretable because the prior knowledge that we use is derived by a human. So as a result, the deep model that uses this prior knowledge becomes more interpretable to humans. So the knowledge augmented computer vision consists so this is a visual illustration of this knowledge augmented computer vision. Traditionally, we have a deep model, right? We have input, then we have training data, bottom-up training data. Then the input, that this training data is used to train the deep model. But what we propose here is we also have some prior knowledge from different sources that provide a top-down training of the deep model. And then we propose different methods to integrate the prior knowledge with the training data to generate the final output. So this is the basic of diagram to illustrate our proposed knowledge augmented computer vision. So now let me talk about what are the major research topics for the proposed research. There are two major thrusts for the proposed research. One is knowledge identification. The other is knowledge integration. The knowledge identification, the goal is to identify prior knowledge from different sources. We want this prior knowledge to be generic, applicable to different domains, different conditions, and we want this knowledge from different sources, not from a single source. Second, we need a method that can integrate the identified knowledge into the deep learning model so that we can integrate knowledge with data to achieve this generalizable, data efficient, and interpretable visual understanding. So first, let's look at the knowledge identification. The knowledge identification, we propose to identify the knowledge from two sources. First is the computer vision models. So these are the series, the models that have been developed in the past 50 or 60 years that they represent the formal theory and the principle that govern the generation of the 2D image from 3D things. So this is the theory, the models, right, related the 3D object with the 2D image. And these kind of computer vision models are very general, very generic, and they should be used and incorporated into the deep learning model. The second is the target knowledge. This is the second source. And here we are interested in the theory of study from different disciplines about that govern the behavior and the property of the target object that we intend to predict or recognize. Again, here we are talking about the generic, well-established theory and studies that are applicable to different objects, to different situations and different domains. So first, let's look at the computer vision models. So over the years, many computer vision models and the theories have been developed. For example, we have the photometric models. The photometric models basically relate the 3D appearance of object to their 2D image appearance. And within the photometric model, we have the illumination model. The illumination model relates the 3D, the illumination object shape with the image intensity. And there are different illumination models. The simplest is a Lambertian model. We also have a bidirectional reflectance map, and we also have more sophisticated illumination models, such as sphere harmonic model. And once we have the illumination model, then we can incorporate the illumination model into the render equation. And this allows us to integrate the illumination from different directions to generate the intensity for each pixel. And this illumination model and the render equation are used extensively in computer graphics to generate photorealistic synthetic images. So this is the photometric models. Then there's also projection models. The projection models basically relate to the 3D object shape and position with their 2D image shape and position. And it can be single view and it can be multi-view. For example, the single view, we may have a full perspective projection model, weak perspective projection, often orthographic. And this is the equation for full perspective projection model that relate a 3D coordinates through a projection matrix to generate the 2D image coordinates. So this is from a single view. We may also have a multi-view projection model. The multi-view projection model relate the image from different views. For example, we may have two views here, right? And if we have two views, then we have a fundamental equation, epipolar constraints, homography. So these models relate the corresponding points on two different views. But if we have three views, then we can use the trend tensor. The trend tensor can relate the images from the corresponding points from three different views. And if we have even more views, right, we can use the latest ecological optical series that relate the corresponding points from multiple views. So these are the theory about projection model. And finally, we also have motion models. The motion model basically relates the 3D motion to the 2D image motion. And the 2D image motion is typically calculated as the optic flow. And this is a differential equation that we used to estimate the image flow, to estimate the optic flow in the image. Once we know the optic flow in the image, then we can perform structure from motion. The basic idea is that we can recover the 3D motion and the 3D structure from the image, from the optic flow of a sequence of image. And one of the very well-known algorithm in computer vision is the factorization algorithm. That given the measurement for image optic flow, we can recover the 3D rotation and the 3D structure. So these are collectively are the computer vision models. They are developed over many years and they serve as the theoretical basis for traditional computer vision algorithms. and they are very general, and they are very applicable to different objects, different conditions. They should be incorporated into the deep learning model. And then the target knowledge. The target knowledge represents the law, the theory of studies from different disciplines that govern the property and the behavior of the target object. Right? There are, and this target knowledge varies with target domain. For example, in my research, I focus on human-centered computer vision, where we want to understand the human behavior, such as body behavior, right? Body behavior. And then we want to identify any prior body knowledge from different sources that govern the body behavior and the property of the body. So our studies show there are different sources that we can extract body knowledge, including anthropometric studies. They study body parts and body proportions. Body anatomy is a sense of study body structure. And the body mechanicals studies, body biomechanicals study the body joint angles and their relationships. And then we have physics, right? Physics, including the kinematics and dynamics. So all this knowledge from different sources, if we use them collectively, and they can provide strong supervision for the training of the deep model. This is what we want to, and these sources of knowledge are very generic. They apply to different body pose, different body shape, and different body motion. So we want to use them to supervise the training of the deep model. So the second step for knowledge, for the proposed is a knowledge integration. So once we have identified the knowledge, we need to integrate knowledge into the deep model. So knowledge integration is to integrate the prior knowledge into the deep learning to ground the deep learning model in a well-established prior knowledge. Knowledge integration into the deep model, however, is challenging. There are two main challenges. The first challenge is that knowledge exists in different formats. They are represented in different representations. For example, the computer vision model or the physics series are often represented as mathematical equations, including the polynomial equation, differential equation, integral equation, and the algebraic equations. So this kind of representation of the computer vision model and theory are precise and exact. On the other hand, the target knowledge that we're interested in to use, such as the semantic relationship and dependency among the target variables, may be expressed as constraints or graph or even logical rules. And this kind of knowledge tend to be qualitative and inexact. So our method that for integrating knowledge into the deep model must be able to handle both types of representation, exact representation and the qualitative representation. And another challenge with knowledge integration is that knowledge is often incomplete, ambiguous, and as a result is uncertain. So our method to integrate knowledge must be able to handle this uncertainty in knowledge, and more importantly, to evaluate the impact of this uncertainty in knowledge on the prediction performance. So this is the challenge that we're facing for integrating the prior knowledge into the deep model. To address these challenges, we are proposing 4 levels of integration. We propose integrating the knowledge in the decision level, in the training level, in the architecture level, and in the data level. So first, let's look at decision level integration. The decision level integration is straightforward. Basically, for a particular problem, we're going to build 2 algorithms. One is based on the traditional model-based vision algorithm. And then we have another learning-based vision algorithm. And each of these 2 algorithms produce their separate independent prediction of the output given the input. Then their prediction are combined through a joint top-down and bottom-up inference. And it is our belief that the combined prediction is going to outperform the prediction by each algorithm alone. And here is a visual figure illustrates the decision level integration. Basically, we have an algorithm that is a model-based vision algorithm. Given the data, we feed the data into the vision-based, model-based vision algorithm. It's going to predict a top-down prediction. This is YM, is a top-down prediction about the final prediction. So we call this prediction as a prior estimate of the final prediction. And then, given the same input, we feed it into the neural network. We generate a bottom-up estimation of the prediction, final prediction. So this is serves as a likelihood. Then we can perform the joint top-down and bottom-up inference by combine the prior with likelihood, use the Bayes rule to generate a posterior distribution of the prediction. And then the final prediction can be derived from the posterior distribution. So this is the basic idea of the decision level integration. And we believe that this, by combining these two predictions, we will end up with a joint prediction that is better than using the prediction from each algorithm alone. So this is decision level integration. The second is training level integration. The training level integration, the basic idea is to incorporate the prior knowledge into the training of the deep model. So this is, and for this, we're going to propose two different approaches. One is the weakly self-supervised learning. The basic idea is we use vision, model-based vision algorithms to produce weak labels. And then use these weak labels to pre-train a deep model. So that's the basic idea of weakly and self-supervised learning. The second is the model regularization. And here is that we want to incorporate the knowledge into the loss function of the as regularization terms. So this is the two different approach for training level integration. So first, let's look at the weakly self-supervised learning. So this is the basic idea, right? We still have a model-based vision. So this is the vision developed based on the theory, right? And for a particular domain, we may have a lot of images, but we do not have labels. So what we can do is that we can use this model-based vision to produce a lot of labels. But these labels are not good, they are weak labels. But we can generate a large, automatically generate a large quantitative labels, weak labels. Then these weak labels, plus with the input data, will be able to use to pre-train the deep model. And once we pre-train the deep model, then we can fine-tune the pre-trained model on the target data set using a small amount of training samples. So this way, we'll be able to generate a deep model that can perform well on the target data set using only a small amount of training data from the target data set. So this is the basic idea of weakly self-supervised learning. The second approach is model regularization. The basic idea is that we want to convert the knowledge about the target variable into constraints, and then implement these constraints as regularization terms in the loss function. So the first task is to convert the target knowledge into constraints. And we can have variable constraints. For example, we may have some linear equality or inequality constraints on a particular target variable. Let's say this is a inequality constraint, linear inequality constraint on the case target variable. And this is a linear equality constraint on the case variable, right? So these constraints are linear equality and linear inequality, but we can also have a nonlinear equality or nonlinear inequality on a single target variable or on all the target variables. And in addition, we may have implicit equality constraints on the target variable. For example, we may have an equation, a function here that involves the target variable and some coefficient alpha, and we assume this alpha are known, right? Then given this function equation, right, and this function actually imposes some implicit constraints on the target variable. And this function can be an algebraic function, can be a differential equation, and can be an integral equation. So this function provides implicit constraints on the target variable. And besides, we can also have a probabilistic constraints on the target variable. Besides the deterministic constraint, we can also have probabilistic constraints. For example, this is a probabilistic constraint on a single target variable. and this is a probabilistic constraint on the two relationship between two target variables. And we may even have a joint probability distribution on all the target variables. So basically, here we try to show you that we are able to convert the target knowledge into constraints. It can be deterministic constraints, can be probabilistic constraints, can be equality constraints, and can be inequality constraints, and it can be explicit constraints or can be implicit constraints, right, on the target variable. So that's basically complete the first step. Once we have the constraints, the second step is we want to construct or implement the regularization terms from the constraints. For example, let's say we have a linear inequality constraint, right? And this is a linear inequality constraint. And we want to implement it as a regularization term. So what we can do is we can put the C on the right to the left. We can have AYK plus B minus C. And then we can construct this regularization term using this minimum function, which consists of two arguments, 0 and the second argument is AYK plus B minus C. So this minimum function returns the minimum of these two arguments. For example, if this constraint is satisfied, then this value is going to be bigger than 0, and then this function is going to return 0. As a result, the loss is 0. On the other hand, if this constraint is not satisfied, then this is going to return a negative value. Then this function is going to return the minimum, the negative value. After we apply the absolute, then they become a positive number. So that forms the loss. So this is using the minimum function to implement the inequality constraint. And similarly, we can also use a positive margin variable to change the inequality constraint into an equality constraint. And during the implementation, we can minimize the value of the positive margin variable. So this is how we can convert inequality constraint into a regularization term. And if it is equation constraints, for example, if this is the constraint, then we can simply construct a loss term by using the absolute value, right? And this, if it is satisfied, then this term is close to 0. If this function is not satisfied, then you're going to have a value non-zero that is bigger than 0. So this forms the loss. And for probabilistic constraints, we can use the same minimum operator, right, to construct the regularization term for the non-inequality constraints. But more importantly, if we have a joint distribution about the target variable, then we can form an expected loss function. For example, this is the L. This is a standard loss function, such as cross entropy or mean squared error. And this Y prime is the predicted Y. And this Y is the ground truth Y. But because we do not have the ground truth Y, right? We don't have, but we do have a distribution of the PY. So then we can compute the expected loss of this term over the PY. So this is how we construct this expected loss term without using any ground truth annotation Y. And once we have different regularization terms, we can form this total loss function, right? The first term is a standard data, right? Term, such as cross entropy or mean squared error. The second is the variable constraint. The third one is the equation constraint, and the last one is the probability constraint. And then we can formulate this as a constraint minimization problem to learn the model parameter theta. However, if we do not have any data, let's say we do not have any data, we can still learn the model. This time, the learning becomes a constraint satisfaction problem. So we want to find the parameter of the theta that minimize the violation of this constraint. So let's show you that we can do zero-shot learning, right? If we drop the first term, we can do zero-shot learning. So this is the model regularization through the constraints. Now, the third level of integration is the architectural level integration. So basically, we want to incorporate the prior knowledge into the architecture of the deep model by introducing additional layer, nodes, module, or pathway, or a new activation function. For example, let's say the encoder-decoder is a very well-known deep model. It includes an encoder and a decoder, right? the encoder is going to, given the input, the encoder is generate the latent representation Z, and the decoder using the latent representation Z to generate the, to reconstruct the input. So we can train the model by minimizing reconstruction loss. And in the data, in general, we do not have, the Z have no semantic meaning, right? And both the encoder and decoder are data-driven. However, for some application, if we have we can change the decoder to a physics-based decoder, and using the physics equations, physics laws to perform the reconstruction. And this way, we can incorporate the physics knowledge into the decoder. In addition, because this is the physics laws, right? It also requires Z to become semantically meaningful, because Z must provide some parameters for the physical equations here to solve the reconstruction problem. So this is how we are able to change a component and incorporate the knowledge into the component of the deep model. Another application is, in some application, in many applications in computer vision, we are dealing with structured prediction, such as the multi-labeling problem, where we have multiple outputs, not just a single output. The traditional deep model is going to construct a multiple softmax function for each output, ignoring the interaction, the dependency among different outputs. To address this problem, we can use a graphic model, such as a Bayesian network or a conditional random field, to capture the dependency among the output variables, right? And then we can put this graphic model as the last layer of the deep model to replace the softmax function. So through this one, given the feature generated by deep model, we'll be able to calculate the probability Py given Z, right? And then this probability Py given Z, we can do a map inference within the graphic model. We can do the map inference. That allows us to simultaneously estimate all the output variable at the same time, instead of estimate each output variable separately. And this joint estimation also subject to the dependency encoded in the PGM model. So this shows you another way of alter the architecture, incorporate the dependency among the target variable into the deep model. So this completes the architecture level integration. The final integration is the data level integration. So here the idea is that we want to convert the data and convert the prior knowledge into synthetic data, and then combine the synthetic data with real data to joint train the model. So the synthetic data will act as the surrogate representation of the knowledge. There are two ways we can perform this synthetic data generation. One is synthetic data generation using simulator. Another is synthetic data generation through a procedure that we introduced called the datalization, knowledge datalization. So first, let's look at the synthetic data generation through the simulators. The basic idea is to encode the knowledge, whatever knowledge we have, into the simulators, and then run the simulator to produce synthetic data. And for computer vision, typically we have two simulators. One is the physics engine. That's the physics engine. It encodes the physics laws, such as the kinematic dynamic laws, that can be used to generate 3D objects with different physical properties, including location, velocity. So this is the physics engine. In addition, we also have a graphic engine. The graphic engine encodes the computer vision model and series, including the projection model and the illumination models, right? And it will be given a 3D object generated by the physics engine. It will be able to render a synthetic image through the graphic engine. So given these two simulators, we can randomly generate a 3D object of certain physical property, feed into the physics engine. Then it can render the image under different viewpoints, different camera parameters, and different environmental conditions. So this is using the simulator to encode the knowledge, and then run the simulator to generate synthetic data. Another approach is what we introduced called the knowledge datalization. So for some type of knowledge, may be difficult to incorporate using other methods we introduce. So what we can do, for example, we have this equation knowledge and this algebraic, this inequality constraints on the target variable. So what we can do is we want to convert this knowledge in terms of equation and the constraint into pseudo data and through a sampling process. So we want to sample the target variable, right, to make sure the samples can still satisfy the equations and the constraints. To perform the efficient sampling, because this Y can be many variables, can be a high dimensional space, right? To perform efficient sampling, we propose to use a MC sampling method, right? And for this sampling method, we want to use a special, to build a special proposal distribution. So this is the sample for the nth sample, and these are the sample we have collected so far. So we want to compute this probability of Yn given all the sample we collect so far. And this consists of two terms. First term is just a constant term for the Gaussian distribution. The second term basically is a Gaussian distribution. Basically, we want to use these samples we have construct a Gaussian distribution. Then we subtract the second term from the first term. As a result, this proposal distribution is going to have a high probability for the regions that with few samples, and for low probability for regions with many samples. So this encourage we collect next sample from the region where there are not many samples, right? Then use this proposal distribution, we'll be able to generate sample. And then we try to make sure the sample is consistent with the knowledge. And then we accept this sample with the probability P. And this continue, and we're going to collect a lot of samples. And these samples become a surrogate representation of the knowledge that we have. For example, in this case, for example, we have a lot of constraints on these three target variable, x1, x2, x3, but they are different inequality constraints. If we try to implement them as directly into the loss function, it may be difficult, right? So what we can do is that we follow this datalization procedure, generate the samples. So these are the sample, and these samples satisfy all these constraints, and then we can use these samples to train the model. So this is the basic idea for. So this basically complete the discussion about the methods that we use for knowledge augmented computer vision. So now I want to give you two use cases to further illustrate how we can implement these methods. First is we want to do 3D human body shape and pose reconstruction from monocular videos. Here we want to demonstrate we can use the body knowledge as a supervision to train a deep regression human body model for 3D body reconstruction. The second is another typical problem in computer vision is 3D reconstruction from a single image. Here we want to show you that we can use the computer vision model, including the projection illumination model, to help train a deep model. So for 3D body shape and pose reconstruction, we follow the deformable mesh model. And this is the typical method in the deep learning model to train this kind of method to recover the 3D mesh. You have input the image, then you go through a backbone model to generate the features, then go through the regression, then you can predict the parameter of the mesh, which includes the pose, the shape, and some camera parameters. And from these parameters, we'll be able to generate the mesh. And from the mesh, we can extract the 3D skeleton, right? So this is the process. However, to train this model, the term typically, the loss function includes the two terms. The first term is the projection loss. Basically, we project the 3D skeleton to the 2D image and then try to minimize the difference between the project skeleton with the image skeleton. So this is the 2D. So this requires 2D annotation. But more importantly, there's a second loss term. This is a 3D annotation. The 3D annotation requires to have the ground truth, pose, and shape parameter for the mesh. And then we can minimize the difference between the predicted mesh parameter with the ground truth mesh parameters. And this term requires the motion capture data. We need the motion capture data in order to get the ground truth shape and the pose parameters. And collecting the motion capture data, first is expensive. The second, it has a limited diversity in demographic and in pose, because this kind of data is typically limited to a certain group of people. And the body shape and the body pose are also limited. So as a result, if we use this kind of motion capture data to train the model, right, it may not generalize well to different people from different group or different body shape or different body pose. In addition, the existing method typically is frame-based. It ignores the dynamics in the body motion. So what we try to do is that we want to use the generic body knowledge to replace the 3D annotation used from the motion capture as the supervision to train the model. And we have a generic body, the knowledge, static body knowledge. We also have a dynamic body knowledge. We will use both static and dynamic body knowledge as a supervision, right? And because this knowledge are generic, applicable to different body shape, different people, and they can generalize better than using the 3D motion capture data. So this is what are the generic body knowledge? So for example, there are different sources that we can generate knowledge about the body. The first source is anthropometry. This is a study based on large amount of human body analysis, right? So this is a scientific study of a human body about the measurement and proportions. And it basically is about the body parts and their proportions. So they give you each body part, its length, the proportion of the body length, the part length. So this kind of proportions are general enough, applicable to different body. And then we have a body biomechanicals. And it is a study about the body joints, right? And it specifies the degrees of freedom for each body joint. And it also specifies the range of the joint angle. And it also provides knowledge about the relationship among the neighboring body joints. For example, these three body joints all have a 3 degrees freedom, or all have a freedom. But this joint only have 1 degree freedom, right? And these two joints are neighbor joints, they depend on each other. If you move one joint, you're going to also change the value of another joint. So this is an inter-joint dependency. In addition, you can see that there's a range. I don't know whether you can see that. There's an angle range for example, for this elbow joint. So this is the biomechanical constraints. In addition, we also have a body geometry. So this basically give you the information about the geometric relationship among the body joints. For example, some of the body joints may be collinear, some of the body joints may be coplanar. And the body joints are symmetric with respect to the left side and the right side of the body. Then we have a body physics constraint. And one of the most used physics constraint is a non-penetrating constraint, which means the body part will not penetrate inside another body part, right? So this is called the non-penetrating body constraint, and this is widely used. So all these constraints are what we call the static body constraint. In addition, we are also interested in the dynamic body knowledge. Specifically, we want to have the body dynamics. The body dynamics basically relate the joint motion with the joint force, right? So this is typically related through the Newton's, for example, the second Newton's law, or through the Euler-Lagrange equation. It relates the motion, the speed, the acceleration of the joint to the tops of the joint torque. So we have this static and dynamic knowledge. So now, how can we incorporate them into the training of the deep model? For the static knowledge, we're going to encode them as the regularization terms, right? So we can build different regularization terms for different type of body knowledge. So this is a regularization term from anthropometry. And this is the regularization term for the geometry, coplanar and the coplanar and collinear. And this is the loss term that we can build for the biomechanical that restrict the degree of freedom of each joint and their range. And finally, we have this term that implement the non-penetrating constraints. So this basically, we can incorporate this as the regularization terms into the loss function to train the deep regression model for 3D body reconstruction. And for the dynamic, what happens if we have a dynamic constraints, dynamic knowledge, then we're going to implement the using the Euler Lagrange equation, right? Euler Lagrange equation in the generalized coordinate system. So this Q is a generalized coordinate system representing the pose, the shape, and some global translation. And this M is the generalized mass, and this C is some gravitational force, and the J is the Jacobian matrix, and lambda is the ground reaction force from the foot, and the tau is the joint force. So we want to incorporate this into an encoder-decoder model. Specifically, we have the 3D mesh, right? 3D mesh. And then we do a mesh convolution. And then we do a dynamic regression from the result of a mesh convolution to predict the force, the ground reaction force, and the joint force. And then we use a deformable mesh model, right, to produce other parameters, generalize the mass and this C from this, the physics parameters. Then we feed this into this ODE solver to solve this Euler Lagrange equation. Through when we solve it through a forward simulation, we'll be able to predict the generalized coordinate in the next time, t+1. And then we can build a dynamic reconstruction loss. This is the predict reconstruct the coordinates in time t+1. This is the input, right? We can construct a dynamic reconstruction loss. And then we can learn this model by minimize the reconstruction loss. So this allows us, if this model is trained, it allows us to predict the joint force and the ground reaction force. So now we put them together. This is our overall framework, right? So first we have a kinematic branch. So this is basically, we want to, given the input, we have kinematic regression. We want to estimate the pose, the shape parameter of the mesh. We use this loss, right? These are the loss terms representing the static body constraint. And this is a 2D projection loss. So we do not use any motion capture, right? And so this gives us the initial body mesh. And then we feed this to a dynamic branch, right? It's a dynamic branch implement the Euler Lagrange equation, right? And through this numerical solver, right? And then we can use the reconstruction loss. Then we get a refined 3D mesh. So by alternately minimize this static and dynamic loss, we'll be able to get refined 3D mesh. And in the meantime, we are also able to obtain the physical parameters. Okay, so this is the okay. So here I want to show you a very evaluation of our method, right? So this basically this is a state-of-the-art method. It is trained using the motion capture data. So data, right? And this is it's a prediction error on this human 3.6M dataset. So this is a within dataset performance. And this is our model. We use a 2D annotation plus generic body knowledge. And this is the error that's from our model. They are a little bit worse than this, but this one is only applied to this dataset. But this one, we do not use any annotation, 3D annotation for this dataset. So they are comparable. But if we apply this model to a different, in the wild dataset, and now you can see the accuracy drops significantly for this model. It does not generalize well across dataset. However, our model, the performance also decreased, but it does not decrease very much. So this shows you that and our model can generalize better because we do not require any 3D annotation, which is data-space specific. So this is for this method. So now I think I'm a little bit behind in time. So I'm going to quickly show the second task. this basically is a 3D shape reconstruction from a single image. So basically, we want to reconstruct given the image, we want to reconstruct 3D shape in terms of the surface normals. The learning-based approach, right, basically say, okay, you give me a pair of image and the corresponding annotation of the 3D surface normal. Then you can train a model, right, by learning the mapping function theta that can predict the 3D surface normal from the input image. And this method is cannot generalize well. It works only for this kind of object and certain that appear in the training data and also appear in the shape, certain kind of shape. On the other hand, there's a model-based method, right? The model-based is typically the 3D reconstruction from a single image. This is typically called shape from X, for example, shape from shading, using computer vision model, in particular illumination model. But this method typically is year-post, and it needs to know the illumination direction. So what we want to do is we want to build a hybrid model, right, that combine these two approaches. So what we want to incorporate this computer vision model into the deep learning model. So the first model we want to implement is this illumination model. We want to implement a very simple illumination model. Basically, it is a Lambertian model, right? It sets the intensity of a pixel equals to the dot product of the illumination with the surface normal and multiply by a surface albedo, right? But this equation, however, requires the knowledge of illumination direction, right? So this is the basis for shape from shading. And the second is the projection model, right? So the projection model is that given, this is the full perspective projection, and this is the 3D points, and this is by projection, we can get a 2D image coordinates, right? From here, we get here, right? So what we can do is that we want to build a 3D surface, so we can build a small patch on the 3D, right? And then we can project this small patch into the image. We have an image patch. And then for any 3D points on this patch, right, we can, for any 2 points, we can get construct a line segment. And this line segment must be orthogonal to the surface normal for the patch, right? So this is the 3D orientation of the line segment using the projection equation. And then this is the surface normal. But this equation requires the knowledge of this lambda ij, which is a scale factor, right? So without this lambda ij, we will not be able to use this. But anyway, this provides another constraint on n. So now we can combine the data with the vision models. So what we do is that we're going to have a augmented loss. So the first loss is the data term loss. The second term is the illumination model, right? And the third term is the projection model, the loss from the projection model. But because for the illumination model, we need to know rho and L, capital L, illumination. And for this one, we need to know this lambda ij. So this is, and the last term is just smoothness term, standard smoothness term. So this is the deep model we build. So we have input, we do a convolution, and then we have the features. Then we feed into a fully connected model, right? To predict the scale factor, surface albedo, and the illumination. And then we have another branch to predict the surface normal. And then this put a constraint on this, right? So then we train the model jointly. And after we finish to train the model, we can drop the top pathway. We just use the bottom pathway to perform the prediction. So this is the basic idea. By using this, we are able to incorporate the illumination model and projection model into the training of the deep model. And this is the performance here. This is the result. For example, if we use this convolution neural network without any projection model, and this is on 2 benchmark data set. And this is the projection, this is the estimation error. But once we include the illumination model and the projection model, you can see we see significant decrease in the reconstruction error. And this is a comparison with some state-of-art method. And you can see our method still is quite competitive because all these methods typically are data-driven. And our method, on the other hand, use the vision, projection model, and the illumination model to improve its performance. So in summary, this is what we have done in this work. We introduced a hybrid computer vision model based on combining model-based vision with learning-based vision through systematical integration of prior knowledge with data. we propose two sources of prior knowledge, target knowledge and computer vision models. And to handle the change with knowledge and the data integration, we introduce 4 levels of data and knowledge integration, including decision level, training level, architecture level, and the data level. The experiments demonstrate the hybrid model can significantly improve deep model data efficiency and even perform learning with 0 shot without any data, and improve the generalization performance across dataset, across domain, and improve the robustness, and also improve the model interpretability. That's it. Thank you very much. Any questions?
Thank you, Dr. Shi. That was a great presentation. I know a lot of detail and a lot of information was passed along to our attendees. We do have one question in so far, and just as a reminder, if you have any questions, you can enter them using into the Q&A box you see on your screen. So first question is from J. Michael. He asked if you could give an application example of encoder decoder architectural level and integration.
So you talk about this one, right? This one? This is what you're interested in oh, sorry.
Yeah, they want an example of an application example of encoder and decoder.
Okay. We have this example actually. We have this example. For example, here, right? In this model here, let me quickly forward this. Okay. So in this here, I think this here, right? In this here, you can see this is an encoder decoder model, right? So this basically is an encoder, right? Encoder generated the features and then do the regression. So this is the Z, and this is the decoder, right? And which encode the ODE solver, solve the ODE equation, right? And the input to the decoder is the physics parameter, the force, joint force and ground reaction force, and also some other physics parameters from the deformable mass model. So this is the example that we incorporated the physics solver into the decoder for reconstruction.
All right. All right, the next question. In the learning-based 3D body reconstruction part, you used ResNet 50 architecture. Can I learn if there is a specific reason why you used this DL model?
This is just an example. It doesn't matter. We can use any latest backbone, right, model to generate features. The basic here is we want to generate a good feature representation of the input image, then go through the regression to estimate the mesh parameters. So this is just for illustration purpose. It's not necessarily the only one we use.
All right, perfect. And let me just check. That looks like all of the questions. Thank you, everyone, for attending and listening to the presentation, for providing some really great questions today. And thank you for Dr. Shi for sharing his great knowledge on this topic. Real quick, before we wrap up, quick programming note, as we have a few more webinars scheduled between now and the end of the year. The next one is on November 15th from on how to manage up from our Build Your Career webinar series. The next one is on December 5th from our Standards Activities Board and the Software and Systems Engineering Standards Committee. And they just released the new Series 7000 standard. So that's going to be more of a panel, and they're going to be talking about that. And then on December 7th, also from our Build Your Career webinar series, we'll have a topic on conversations with senior management. Registration for all these webinars is now open. You'll be able to register using the link you'll receive. With the link you'll receive tomorrow, the email, that will also include a recording and a copy of today's slides. Thank you again, everyone, and have a great rest of your day.
So shall I stay here?